Okay, so coloring planar graphs. Okay, so actually there's two options when you color planar graphs. I mean, or there's actually more than two, but for now we've been coloring vertices and that's been the thing to color, but you can also color faces of a planar graph. So we can color vertices like we've been, or faces of a planar graph. Actually, you can color edges too. That's something we'll talk about probably next week, or maybe on Friday we'll start talking about that. But we're not interested in that for planar graphs. And with planar graphs, yeah, I mean, so before vertices was the thing that we colored, we've been dealing with that completely, but faces are well defined in planar graphs. And so you could color those instead. And the rule for coloring faces is pretty obvious, right? Two faces that share an edge between them, that share a boundary, should get different colors, right? And actually, this is pretty like famous question, thinking about coloring the faces of a planar graph. This is the same as coloring like the map of, you know, a country, of like, say the United States, coloring the states so that you get a nice picture, right? You don't want two states that are next to each other with the same color, because then you can't distinguish them, right, in a map here. But it turns out that answering this question is equivalent because of the fact that graphs and their duals are both, I mean, planar graphs and their duals are both planar graphs. So like if I give you a theorem that like, hey, every planar graph only needs 12 colors, then how do you color the faces? Oh, just dualize it and color the vertices of the dual, right? But the actual required number of colors between those two things, that may potentially vary. Let's just look at a picture here. I'm going to be talking about coloring vertices today, just because the machinery we built up makes more sense. But being aware of the face coloring problem is important and interesting here. So say, let's look at this graph here. I'm going to draw two instances of it. We're going to color its vertices and then its faces. Something like this. So let's color vertices first. I'll do that on this picture here. What can you tell me about the number of colors I'm going to need if I color vertices? At a minimum. Yeah, I'm going to need 4 at least, right? I've got a complete graph on 4 vertices in there. So no matter what I do, I'm going to see colors 1, 2, 3, and 4. In that arrangement or some permutation of the colors is the same thing. And then this last vertex, I have a lot of options for it. Let's say it's 2. The point is I didn't need another color here, right? So chi here is actually equal to 4, right? It's at least 4 because of the complete graph, and it's at most 4 because I exhibited a coloring with 4. But then if I look at the same graph here and color faces, I think I can get away with 3 on this one here, right? I can do 1, 2, 3 for those 3 faces. Color this with color 1 again, because these don't share a face. And then color the outer face with 3, because this face of 3 is kind of stuck inside of there, okay? So on the faces here, I got away with 3 colors. But all that means is that the dual of this one, which is a different planar graph, only needed 3. I mean, we could look at it real quick, I guess, right? So the dual is draw a point inside of each face, and then draw edges between them. Did I get everything? I think I got everything here. And then this red graph here is a planar graph, but it's a different planar graph. And you can see that we can get away with 3 colors on the vertices of that. I mean, that's equivalent to coloring the faces. Okay, so making a general rule about the number of vertex colors needed for a planar graph would tell us a general rule about the faces. But that doesn't tell you, like, the graph and its dual are 2 different planar graphs in general. By the way, you do have planar graphs that are self-dual. But yeah, so anyway, we're going to focus on vertices today, because in some sense, what we can say about these answers it for everything. Although again, it doesn't tell you specifically the chromatic number of the dual. Okay, so yeah, let's say, let's just say this as the dual G star is planar. These 2 questions are equivalent, essentially equivalent, right? Not for a concrete graph, but for a general question about what's the chromatic number of planar graphs. Okay, so let's start off with a proposition. We only call it a proposition, well, one, because it's simple to prove, and two, because we're going to replace it with a stronger theorem in a moment here. But this says every planar graph is 6 colorable. Okay. So no matter what your planar graph looks like, 6 colors suffice to color the vertices of the planar graph. Okay. And this is somewhat interesting because this is a constant, right? We've seen so far all of the bounds that we had on planar graphs, like Brooks's theorem and so on. The upper bound was like delta, was the max degree. Now I told you that certainly that's just an upper bound. The chromatic number may be well below delta, but in a planar graph, you can have high degrees, right? A planar graph can absolutely have a vertex of, like, just as an example, here's a planar graph, take a long cycle here and just draw tons of spokes here, right? That's a planar graph with a very, very high degree. Actually, this graph only needs 3 colors though, right? High degree doesn't guarantee. Okay, it might need 4 colors if you have an odd cycle, but whatever. It's still low, right? So high degree doesn't guarantee high number of colors, and we know that like cycle lengths don't force lots of colors either, based on the these theorems the graphs from the Hall of Fame type theorems. But we still have this rough idea that we need edges, lots of edges, to force chromatic number up. Actually, we didn't investigate that specifically last time, but last time, maybe it's worth saying, remember in the graph that Erdős constructed probabilistically, we had a probability P, and then we had n vertices, so n choose 2 pairs of vertices. You're going to have this many edges in that graph there. And remember P's order, it was something like t minus 1, so it was something like, sorry, that's P was equal to this, which was something like, let's just say like 1 over g minus 1 here. And so if I multiply this by this guy here, this n squared, I get number of edges that's something larger than linear in n, right? Like multiplying this times p squared, you get n to the 1 plus 1 over g. So not linear, right? Not linear in n, it's something bigger than linear in n. But the number of edges in a planar graph is at most linear in n, right? It's at most 3 times n minus 6. And somehow that has a lot to do with it. That's not the whole story, actually. You'll see planarity itself, not just the number of edges, is crucial in the proofs. But the point is, planar graphs are sparse graphs. They don't have a lot of edges, generally. I mean, they don't. And that seems to suggest that they shouldn't need a lot of colors. But let's prove this. It's not enough to just, think that it seems true. Okay. All right. So the technique we'll use in this and all the proofs today is that we're going to look at a minimal counter example. Okay. So let G be a vertex minimal counter example. Okay. Maybe I haven't used the following term in this class. I hope you guys have seen it in a proofs class somewhere, but we like to call these things a minimal criminal, right? I love that term. We don't really need it for graph theory. I use this in like 225 to introduce the notion because it's very, very memorable, but it's worth saying from time to time. Okay. So if G is a vertex minimal counterexample, then it means that the theorem holds, or the proposition holds, for any subgraph of G, proper subgraph of G. Actually, let's say after I remove a vertex, it's better, we should say, because I didn't say edge minimal. So then G minus X is 6 colorable for any vertex X. Okay, that's the key takeaway here. If you have a vertex minimal counterexample, if I pull off a vertex, that new graph has fewer vertices. It's no longer a counterexample because I had the minimal one here, or a minimal one here. And so it actually satisfies the proposition. So it's 6 colorable, right? As you guys probably know, minimal counterexample arguments or minimal criminal arguments are basically inductions in disguise. So what am I using? I'm using that G minus X is 6 colorable, and I'm going to arrive at G being 6 colorable, even though it was a counterexample. I'm actually going to give a 6 coloring. Okay. And so the key to this observation here is I can remove any vertex and get a 6 colorable graph, but let's be smart about it, right? Because say I pick off a vertex X that has like a really high degree and say, hey, here's G minus X, and it's 6 colorable. How do I, up that to a 6 coloring of the whole graph G? Well, I can, unless I see all 6 different colors adjacent to X. Then it's like, well, how do I fix it? In fact, we encountered this already in a proof of Brooks' theorem. And in Brooks' theorem, we're like, okay, if you get that, shift some colors around and we can still fix it. But here I can do better. I can carefully choose X so that this is okay, all right? So what can you tell me what X would work if I could find it, right? So, I mean, okay, maybe this drawing isn't good here. Because there's not, I need like six edges coming out causes a problem, right? So maybe the C is color 1, 2, 3, 4, 5, and 6, right? There's vertices like this. And then the question is, how do I color X in that case? But how could I choose, or what X would be better? Like what property of X would allow me to extend the coloring? Yeah, can we find an X of degree less than 6, right? Degree 6 X is problematic because in the coloring of G minus X, which is done by, black magic, it may get colors 1 through 6 on its neighbors, and then I can't extend it to X. But if X only had 5 neighbors, then it didn't matter what colors they got. They could only absorb 5 of the 6 colors, and I'd be safe to choose X. So I just need to find a vertex of degree 5 or smaller, okay? So the question is, does G have a vertex of degree at most 5? Okay, so that's the question I want to answer here. And the truth is yes. Suppose not. So if it doesn't have a vertex of degree 5 or smaller, all degrees are at least 6. Then all degrees are greater than or equal to 6. And then what's the sum of the degrees of the graph? Well, it's at least 6 times the number of vertices, right? If every degree is at least that, which implies that the number of edges of G is at least 3 times the number of vertices, right? Sum of the degrees is 2 times the number of edges. Handshaking lemma here. So the number of edges is at least 3 times the number of vertices. And what's going on here? There's a problem here. This violates the planar edge bound, right? This is strictly more than, of course, 3 times the number of vertices of G minus 6. But this is the most I could have. This is max in planar graph G. So I have a contradiction, right? If every vertex is 6 or greater, then the sum of the degrees is too big. So it means I definitely have a vertex of degree 5 or smaller, okay? This observation here that we have, so okay, let me write this, just write this down again, because we're gonna use this in the other proofs. A planar graph G has a vertex of degree at most 5. I'm gonna box this. All right. This is true for any planar graph. It's not just used in this proposition. We could have proved this as a separate lemma originally. In fact, very often in textbooks, this property will be given soon after you prove the Euler characteristic equation. You get Euler characteristic, we use that to prove the edge bound, and then this follows from the edge bound. It's just a corollary. So it holds generally. And how do we use that here? Well, I mean, I already explained it, but let's just go through it real quick. So let X be a vertex of degree 5, and then just remove it. And 6 color G minus X, right? G minus X is smaller than the minimal counter example. So I can color it, maybe we draw it like this, right? So here's a planar drawing of G, and then I remove X. And X had at most 5 neighbors. In this illustration, I put 5. It might have 4, 3, or 2 neighbors. Those are all just fine as well. So draw the planar graph of G here. Actually, we don't even need to draw it. We don't need to draw it, right, at all. G minus X is still planar, right? So it's not a counter example because it has fewer vertices. So it has a 6 coloring. Give the 6 coloring of G minus X. So just forget this version here. We can use this one here, G minus X. Give the 6 coloring, and then look at the potentially 5 neighbors of X. Even in the worst case, they only see 5 of the 6 colors available to me on my palette. So there exists I'll call it safe color for X. In other words, G is 6 colorable. And I mean, that's technically a contradiction to the fact that it was a minimal counter example. as I've discussed before, this is kind of the most annoying type of counterexample, because the counterexample is that I achieved the thing that I wanted in the first place. But you see why setting this up as a contradictive proof was quite valuable, because it gave me for free a 6 coloring of G minus X. Without that, like, how do I extend it? Maybe G minus X wasn't 6 colorable, right? So yeah, but nonetheless, despite that sort of awkwardness, which is perfectly legitimate, it's just something I personally don't like. we finished the proof here. If you don't want that, you can go through and do this by induction directly and make it work. You have an example on, say, 4 vertices that can be colored with 6 colors, actually fewer, and then just do induction using the same argument there too. But using induction when you don't need to is just as awkward. So like you can't win. It's a beautiful proof though, nonetheless, right? So okay, so let's immediately replace it with an improvement. So actually, planar graphs are 5 colorable. Okay, but yeah, but the technique is similar, and this is important to be established. We're going to use this fact again here. Okay, so now we know the 6 colorable. Let's improve that. Okay, theorem. Okay, I'm going to name it. This is called the 5 color theorem. It's by someone called Kempe. I don't know. It's 1880s maybe. I mean, this is, I don't usually include this information, but yeah. So every planar graph is 5 colorable. Okay. Yeah, just keep in mind, what does this mean? It means that the chromatic number of the graph G, the planar graph G, is at most 5, right? It might be fewer, of course. We already saw examples of planar graphs that were 3 and 2 chromatic. An even cycle by itself is 2 chromatic and planar, and so on. But Kempe's theorem here says you never need more than 5 colors. Okay, and the proof is similar to the above with a really, really cool observation or trick. Okay, so again, let G be a minimal, vertex minimal counterexample. Okay. And now let X be a vertex in G of degree at most 5. Right, we know this exists by the boxed lemma from the previous thing. There are definitely vertices of degree at most 5. Okay. If X has, or if, so, okay. Yeah, okay, let's just say if X has degree at most 4, say it's even smaller, then we can actually get away with what we want here. Okay, I want to rule this out. We don't actually need to do this separately, but I want to make an additional conclusion in this theorem that's sort of interesting about this potential minimal counterexample, because it'll be relevant later. So suppose that X was degree at most 4. In other words, suppose there was a vertex of degree even smaller than 5, say 4 or 3 or 2 or 1 or even 0. If you have this property, then you can't be a minimal counterexample, right? Because this one will clearly be colorable. Okay, so G minus X is 5 colorable, right? By the fact that G was a vertex minimal counterexample. So here's X. Here's again G minus X. And if X only sends 4 or potentially fewer edges across here, then there's a safe color for X, right? 1, 2, 3, 4. It sees at most 4 colors, different colors in the coloring of G minus X. And therefore, X has a safe color, okay? So in this case, if X is degree at most 4, then G is 5 colorable, which is actually a contradiction. Okay, it actually contradicts this fact here. So actually, what does this tell us about a minimal counterexample? It has a vertex of degree at most 5, and what else? It doesn't have vertices. Yeah, Ethan, go ahead.
Yeah, every vertex has degree at least 5.
Yeah, exactly. Every vertex has degree at least 5. Exactly. Okay. So every vertex has degree at least 5. That's what we can conclude. we don't actually need this information in our proof here. I just wanted to make this important observation. The point being is if we're looking at a vertex minimal counter example, we know they don't exist ultimately because we're trying to prove a theorem that shows they don't exist, but we can start to build up information about what they might look like, right? And that's good. The more you know about your vertex minimal counter example, the more options you've got to find a contradiction, right? You find things that just aren't possible, okay? But on its own, at least now, there's no contradiction, right? Every vertex being degree at least 5 and potentially having some higher degree vertices, that doesn't violate the planar edge bound yet. It's not enough information, right? We need them all to be like in the realm of 6 to do this. This can rule out certain things, like you can't have too many vertices at degree 7 and things like that, but that's not enough for us to get anything. Okay, but the point is, if I pull off a vertex X like this, I'm going to get 5 neighbors over here. And actually, we know another thing. We know still G minus X is 5 colorable. And we know that when I do that, I'm going to see all 5 different colors on the neighbors of X. Otherwise, I can extend the coloring. Same thing. In fact, let's do that. Yeah, let's start looking at pictures again here. So let's look at G minus X again. And now I'm going to start to think of it as being drawing planar, because that's going to matter, right? In the previous theorem, we didn't actually use planarity, right? Let's jump back for 1 second. This is worth asking. What property did we actually use in this theorem here? We didn't really use planarity. What property mattered here? It followed from planarity, but you could have it without planarity. What did this rely on? Anybody see it?
Every vertex had degree. There was a vertex of degree less than 5.
Yes, exactly, Ethan. All we needed for this to get 6 colorability was the existence of a low degree vertex, right? A vertex of degree 6. And, together with the fact that it was a minimal counterexample, that the remainder was colorable here, right? We never used that we could draw it in a planar fashion. Like that property was not used. It was just what was used was this information that my edge bound, I had at most this many edges that gave rise to a vertex of degree 6. That's all that I actually needed. Yes, that's a consequence of planarity, but there are non-planar graphs. We've even seen them that don't exceed this quantity here, okay? K33, for example. Okay, so here, the improvement essentially in the theorem is that we're going to use planarity that we didn't use before. Okay, so I'm going to look at my picture as follows from now on. Here's X, and then X's neighbors are Y1, Y2, Y3, Y4, and Y5. Okay, and since it's planar, we can assume that they're drawn in a clockwise fashion like this. They don't cross, the edges don't cross each other or anything like that. There's no other crossing edges. There may be stuff inside of these areas, right? Other parts of the planar graph, but as far as X is concerned, its neighbors look like this. Okay. Okay. So the first observation, let's say, is vertices Y1 up to Y5 use colors 1, 2, 3, 4, and 5. Okay, and what I mean by like all 5 colors appear among them, because if not, so otherwise, X has a safe color again, right? Just as an example, I mean, I think this is pretty clear, but imagine the colors were 1, 2, 1, 2. Well, I don't need to be so generous. 4, 2, say. Then I can color X with color 5. I've got 5 colors. If it only sees 4 colors, then there's a safe color. So I might as well assume the colors around it are 1, 2, 3, 4, 5. Okay. In fact, I'll even assume that up to, you can relabel the colors if you want, or the indices here. Y1 is color 1, Y2 is color 2, Y3 is color 3, Y4 is color 4, and Y5 is color 5. We can assume the picture looks precisely like this. Otherwise, we don't have a minimal counterexample. Okay. I don't have enough room, so I'm just going to immediately redraw this picture, but we're going to start working with this picture. And this is the crux of the proof. This is where it gets pretty cool. Okay, so here's X, and then we've got Y1, Y2, Y3, Y4, and Y5. And they see colors 1, 2, 3, 4, 5. I won't write down the color. Well, I will actually, because we're going to use them a bunch here. 1, 2, 3, 4, and 5. Okay, so now my goal here is something similar to one of the proofs of Brooks's theorem. I want to recolor the graph in such a way that X sees a repeat of colors, right? Like if I can change this 2 into a 1 or 3 or 4 or 5, then X will have color 2 available to it, right? If I can get any repeat among these, I can do that, okay? And in what we did in one proof of, it must have been Brooks's theorem, we built up these like different colored paths among vertices, and we had this like whole picture, and we actually want to do something very similar here, okay? So what I'm going to do is, let's let first G1, 3 be induced subgraph of G on vertices of color 1 and 3. So what do I mean by G1, 3? Just take all the vertices of color 1 and 3 and maintain all the edges that were among them already. Actually, we did exactly this in Brooks's theorem, okay? So this is everything. So for instance, Y1 and Y3 are vertices of G1, 3, right? But there's other stuff, okay? So now the first thing is if, I'll maybe say this is an observation here, or claim. So I claim that Y1 and Y3 are in a component of G1, G3, okay? So they're connected to each other by some kind of path. Why is that? So if not, I'm going to prove this by picture. So suppose they're not. So suppose Y1 and Y3, they're both in graph G1, G3, but suppose they're in different components. We use the same reasoning we used in the proof of Brooks theorem. Well, then look, Y3 is in some component of G1, 3, right? This is a component, but it doesn't reach over to Y1. What should I do then in this component? What do we do in Brooks's theorem? Anybody remember the trick?
Swap them?
Yeah, let's swap. Oops. Swap color 1 and 3 in this component. So all 3s become 1s and 1s become 3s in there, okay? This maintains the proper coloring of the graph, right? 1s and 3s see each other inside of this thing, but they get reversed. And if 1 is adjacent to 2 and 4 and 5, and now that it's a 3 instead, that doesn't have any effect, right? The other vertices are still safe. And then what happened now? Now X sees colors 1, 2, 1, 4, 5. Ah, that means I can color X with a new color. I mean, with the color 3, for instance, right? I could have done the swapping up here if I wanted to instead. It doesn't matter. Just choose one or the other in different components. So if not, ... what we argued here, G has a 5 coloring, right? Which is a contradiction. Okay. All right, great. So that means that our claim holds. Y1 and Y3 are in a component together. So let me erase this business here. So if they're in a component together, it means there's a path between them. Okay. So thus, following from the claim here, there exists a V1, V3 path in colors 1 and 3 only, right? Because I mean, I just showed they're in a component of G1, 3, which only sees colors 1 and 3. So let's just draw that in again here. Okay. Oh, I don't know why I erased that. Y3 was color 3. And now we've got a path between the two of them. Let's draw it like this. Maybe it goes around the other way. It just goes around one way or the other, okay? And this path alternates colors 1 and 3. So 1, 3, 1, 3, 1, 3, 1, 3, something like that. Ends up in 1. Excellent. Okay. Now, let's do the same thing. Let G2, 4 be blah, blah, blah. Okay, is it clear what G2, 4 is? It's the graph with colors 2 and 4. You guys see what's going to happen here? Now we're using planarity. So G2, 4 is everything in...
What is the word? opposite contraction.
Oh, like a subdivision. Is that what you're
Yeah.
suggesting?
Yeah, we're gonna get a subdivision.
Okay, that's interesting. We don't actually. Oh, okay, that's a really cool idea. Let's keep that in mind to think about. I don't intend here to get a subdivision, but I mean a subdivision of a K5 or K33. But I wonder if we can actually argue that we get that in this proof here. So let's keep that in the back of our mind. We've got a little extra time here, so let's think about that after I finish it up here. Okay. So let G23 be the graph spanned by colors 2 and 3. Sorry, 2 and 4. 2 and 4. Okay. And then there's two ways to go about doing this, but I'm going to do the one that's like, I don't know, sort of more interesting or whatever. So claim again, Y2 and Y4 in same component of G24. Okay. And does everybody agree that this claim is clearly true because it's exactly equivalent to the claim we made about 1,3, right? If Y4 or Y2 is in a separate component, then look at Y4's component here, swap colors 2 and 4, and then Y4 has color 2 on it, and then X sees color 2 twice, so it's safe to color with color 4. Okay. But the fact that this claim holds gives the same consequence. So now there's a V2, V4 path in colors 1 and 4. Okay, so this implies something similar to before. So there exists a V2, V4 path in G24. That's the same, it's just saying in colors 2 and 4. But where is that path? It starts here and it ends here. So, okay, it's going along like this, 2, 4, 2, 4, 2, 4, 2, 4, 2, 4. How does it get over here? It either like literally just crosses this. Well, it's planar, there's no crossing edges, or it intersects the path, right? That's one way of getting out. In Brooks's theorem, this was allowed, potentially. It was a little, but here, is this allowed? Can this 1,3 path share a vertex with the 2,4 path? No. The vertex on this path is color 2 or 3. Sorry, not 2 or 3. It's 1 or 3, this path here. And this guy's path is 2/4. So they can't share a vertex because it has a concrete color. So I can't get out. So what it means is that this part here onto the 2,4 graph part here is a component. It can't be joined to this guy here. That's using planarity. I can't escape. Once I made this 1,3 path, I trapped vertex Y2. It couldn't get out. So if I swap 2 and 4 in this region here, I'll free up a color for X. Okay, so I either get a contradiction saying they have to cross and it's not planar, or you can, instead of doing this claim, you can observe that the G24 graph has a component inside of this thing that's necessarily separate from this component. And then you just do the color swapping in either. Either way, you get a contradiction, right? Either way, you free up a color for X, okay? These paths, these 1,3, 1,3, 1,3 paths, these are called Kempe chains, okay? Kempe was the inventor of this proof here. So they have the technique is called Kempe chains. And actually we've seen them before. Like I said, in Brooks's theorem, we actually use this technique as well. We just didn't have planarity at our disposal. We didn't, we proved a different theorem, but we used the same idea. Okay, so everybody see this? Here we clearly use planarity. We got trapped, which is, I really think that's a cool idea. Okay, so that ends that proof. I want to think for a second here about what Ethan said, because that's pretty interesting. So I think.
Can you repeat what he said? I can never hear.
Okay, yeah, sure. So what Ethan said was that he was seeing that we will probably get a subdivision of a K5 or of a K33, right? Which would be a contradiction. Planar graphs don't contain subdivisions of those type, and I believe we do get those, right? Let's draw a picture down here again. Here we've got X, and then we've got its 5 neighbors. Actually, we only need 4 in this picture. Right? And we argued that there's a path here. And let's forget about the crossing business. We also argued that there's got to be a path here. Right? And then I was hoping we'd see a K55 here among these 5 vertices. We don't seem to need this one here. But I don't quite see a subdivision because I don't see paths here, here, here quite yet. Maybe we can sit down and prove that they exist. But this is not quite a subdivision, right? Not yet.
What if you attach all the other loops and then try to find a K5 minor?
Okay, that's a good idea. So we can also make, we could make similar arguments. Oh, okay, I see. That's an interesting idea, Eric. So let's look colors 1, 2, 3, 4, say. Let's ignore 5 for now. Actually, I don't think we'll need it here. Now take the graph of colors 1 and 2, right? And then swap colors. 1 and 2 have to be in a component together as well, because otherwise I can swap out. So I can get a path here, I can get a path here for the G23, I can get a path here, and then now I've got a K5 minor here if I continue to do those same tricks there. I just didn't need to go that far because that was already a contradiction. But yeah, I believe the two of you together are right here, that getting the rest of these paths gives a K5 minor or K5 subdivision, which is a contradiction as well. Different approach. That's interesting. That's actually cool. Okay, so this will also end the proof here. Okay, and actually this is really good because this immediately points some question out. Well, wait a minute, like what's going on with this vertex that I didn't even use here? Okay, so I want to talk about the next theorem, which we're not going to prove, but I want to discuss these Kempe chains a little bit further. Okay, so the next theorem is pretty famous. It's probably the most famous in graph theory. It's the 4-color theorem. Okay, so every planar graph is 4-colorable. Okay, and this can't be improved in general, right? There are certainly 3-colorable planar graphs, but in general you can't drop below 4 because of this. The K4 is planar and requires 4 colors. So this is the best you could hope to do in general. Okay, but the proof of this is computer assisted, and the original proof is computer assisted and 400 pages of cases. So you can't do this. And even the most modern proof is still, I think, in the order of 100 pages. There's no elementary proof of this theorem. This is still a major pursuit in graph theory. Actually, I don't know a lot of people that are currently working on trying to find an easy 10-page, 20-page proof of this. But everyone at one point has tried to do this because it's still considered a worthy pursuit. Despite the fact that we believe and know that it's true, finding a new proof or a better proof is very, very desirable. It's sort of unsatisfactory to a lot of people that there's such a long proof for such an easy statement. Although, Fermat's last theorem is a great example of that as well, right? That is a long proof. It'd be nice to have a short one, but it's not clear that there can be. The other thing that was really annoying about this for many people was the early proof was computer assisted, in that it used a computer to check these cases, and people didn't like that either. Although in principle, it was hand checkable. Just if you spent, I don't know, a month, or I don't know how long it took, but we didn't like that very much either. I want to say a couple words about the proof because it's actually pretty interesting, and maybe I'll let you guys think about that. Actually, this is a great exercise. Try and figure out, maybe I'll even put this in a homework, why the Kempe chain argument does not prove the 4-color theorem. Because it seems wait a minute, if you go up to the picture, this one or this one, this didn't even come into play. Why can't I try this alternating trick, with 1 and 3 and then 2 and 4, and argue that actually, if I had 4 colors here, I can reduce it to 3 and get a safe color here. Okay, it's not terribly difficult, but it is a little subtle. In fact, it's so subtle that when Kempe first gave the 5-color theorem, he claimed that he had proved the 4-color theorem using this method, and it was 11 years before someone found an error in the proof. Things operate a little differently then than they do now, but nonetheless, this held as a proof of the 4-color theorem for a long time. So it is a little subtle, but you guys are equipped to definitely figure it out. Even if you can't sort of prove it concretely, although you should be able to, you'll get a feel for even though I never said anything about this vertex, it is relevant here. And there's a very good reason why I chose to swap 1 and 3 instead of 1 and 2. It wasn't arbitrary that I chose these that had a gap between them. That's very important. Okay, but I'll leave it at that. Okay, so I'll say that about the proof. Here is Kempe chains fail. Okay, so they don't seem to work. I mean, okay, maybe there is still a way to do it. That would be very nice, but just copying what we know now or know from before, Kempe chains don't seem to work. Okay, but let me say something about this proof here. So again, I mentioned it's computer assisted. I think it was done in '76. So computer assisted in 76 is different from computer assisted now. Computation time for checking this is short. It's just still like not easily doable by hand. And it's something like 400 pages. Although there's been a more modern treatment since the 90s that's more like 100 pages. I think maybe it's even shorter than 100 pages. This is by Robertson. What? No, Seymour. Okay, whatever. You can look it up. Actually, there's a really good book by Wilson. Like it's an actual book, like 200 or 300 pages on this problem as a graph theory problem, like its history, how it was developed, some of the ideas of the proofs. It's like it's a good popular mathematics book to read, especially if you worked in graph theory. Or, I mean, had a class in graph theory. Okay, but the idea of the proof is it's similar to the previous ones. Actually, the proof goes, so we take a minimal counterexample. Okay, and what we do is we find this list of reducible configurations. Okay, so find what we call reducible configurations. Okay, so what reducible configurations are, they're, let's call them subgraphs. They're not quite subgraphs, but they're basically subgraphs in my minimal counter that can't be in a minimal counterexample, because you can remove them and get a smaller counterexample. Okay, so what is a minimal counterexample? It's a graph. So it's a planar G that is not for colorable, right? And a minimal reducible configurations are things that I could remove from that and continue to have a graph that's not for colorable, right? Like one easy example of a configuration would be this. Like a minimal configuration is not going to have this vertex here, because if it's a minimal counterexample, and that means I can remove a vertex and the remaining graph is for colorable. But then I can, what am I saying here? This is a bad example. This doesn't get right. So what do I want to say here? Okay, I'm just going to say these are subgraphs that can't occur. Okay. Okay, so proving that these reducible configurations can't occur is non-trivial. That's something that is part of what's done in the computer-assisted proof here. So this one's not immediately apparent. It's not simply remove a vertex and you get a smaller example. Let me draw another couple here. Okay, I'm not going to argue that these are reducible configurations. I can't do that. But you can show that a minimal counterexample can have subgraphs like these, say. So it can't have this diamond shape with whatever degrees coming out of them. That's why it's not a subgraph, because there's other vertices. I don't know what the rest of it looks like. But if you have this picture in your minimal counterexample, it's not a minimal counterexample. You can construct a smaller one out of it. Okay, and the point is, and let me give maybe one more because it's pretty. Oh, it's a 5-cycle. And then we can do it this way. I mean, this is ridiculous. This is a K5 that can't be in a planar graph no matter what. This is not the graph I'm trying to draw. It's actually, and then one more here. And then these can be joined up to the rest of the graph, however. So there's this list of reducible configurations that can't occur, okay? And there's like 1,500 of these. Okay, so you can see why this proof is problematic. Actually, I think their first proof was like 1,800, and then they reduced it to 1,500. And the current best, the other proofs of this theorem all use the same technique. There's about like 700 of these things that can't happen. And so in principle, each of these you have to individually argue why it can't happen in a minimal counterexample. And each of those takes a little bit of a proof, although there is a way to set up a computer to be able to check that these can be reduced, but the point is each of these has to be checked. And then the way the proof actually goes is says, hey, in any minimal counterexample, there's a set of what we call unavoidable configurations, things that have to occur. And there's some sublist of these, collections of sublists that you can't avoid. And so you have to have one of these. And so you're not a minimal counterexample, so it's a contradiction, okay? But the bulk of the proof comes from this list is long enough. And certainly you can make shorter lists, but the point is you need a long enough list to guarantee something in that list happens. And that's why this list had to be made so long. they guaranteed something out of this 1800 happens, contradiction. And then, Seymour Robertson and the others were like, you don't need that many. Even on 700, you're guaranteed to get one. Some can be thrown out. They're redundant or whatever. But the point is, it's not a new idea. It's just a cleaning up of the cases. And so that's roughly, very, very roughly, the idea of the proof and what makes it difficult. It uses a method that we call discharging. We've actually seen discharging. If you guys remember, the proof of the Euler characteristic where we assign charges to the faces and vertices and like played with the charges, that's a method called discharging. And that's what's going on behind the scenes here to guarantee that one of these pictures happens. Like you put charges, you move them around, and by the rules of planarity, you kind of have to arrive at certain of these pictures no matter what, which is impossible because a minimal counterexample can't include these pictures, okay? Maybe I'll end it there. It's worth reading about. Like I said, that book by Wilson says a lot more than this, and it's readable to even a non-expert in graph theory, and it gives you an idea of what's going on. It's like it's pretty cool. And like I said, this remains a tantalizing question. I think every student of graph theory at one time was like, I want to prove this without this computer assisted, in 50 pages that'd be a remarkable achievement. So